Hello everyone and welcome to Lost in Transaction, Process Doppelgänging. My name is Tal Liberman. I'm the Security Research Team Leader at enSilo. With me here is Eugene.
Hello everybody, I'm Eugene Kogan, a software engineer also from enSilo.
Today we're going to be talking about Process Doppelgänging, which is a new evasion method for Windows. The flow of the talk is going to be that we're going to start off by briefly covering the history of evasion techniques. We will then move on to speak about AV scanners and all the different considerations one must take into account when developing such scanners, at which point we'll move on to NTFS transactions and a thorough investigation of the evolution of the Windows process loader. Finally, we will overview the doppelganging execution flow, and then we'll see the mitigation in Redstone, the story of a blue screen we ran into while conducting this research. So, advanced code injection techniques have been with us for many years. Notable methods are ghostwriting, atom bombing, power loading, Propagate, which was released only a few weeks ago, and all these techniques allow you to run shellcode in a target process. We also have reflective loading, which is the loading of DLL files or exe files from memory without touching disk, and also we have process hollowing, which is another technique to use a legitimate executable as a container for running malicious code. So let's take a look at some of these techniques. Ghostwriting is, as the author calls it, paradox, writing to another process without opening it nor actually writing to it. It's an injection technique from over 10 years ago, and it hasn't really received much media attention. The goal of ghostwriting is to inject arbitrary code into a process without using open process or write process memory or create remote thread or any of the known injection APIs. The way ghostwriting works is by finding two patterns in NTDLL. The first pattern we'll call the move pattern, and the second pattern we'll call the jump pattern. What we're going to do is use these two patterns to achieve what we call write what where, which is the ability to write whatever data we want into whichever address we want in the target process's address space. Now we're going to do this by first using the move pattern. If we take a look at the move pattern, you can see that the move pattern is made up of two instructions. The first instruction is move to the memory pointed to by a register we'll call reg1, the data or the content that's stored in reg2. Then following that we'll have a return instruction. An example of the move pattern is something like we have here, where we have move to the memory pointed to by EAX, the content of EBX. And the goal here is that we're going to use setThreadContext API, which is an API that changes the values of all the different registers for a thread, to store an address in EAX, for example, and data in EBX, and have the data in EBX written to the address pointed to by EAX. Once this instruction executes, the next instruction that will execute is the return, and at this point we don't really know where it's going to return to. It's unpredictable. So what we're going to do is we're going to use some memory manipulations to have the return jump to this jump pattern. Now, what is this jump pattern? This jump pattern is just jump 0, which means that it jumps 0 bytes, and that means that it will just keep executing the same instruction over and over again, or basically it'll be stuck in an infinite loop. Now, this instruction shouldn't be found in a normal program, because nobody would want their program to completely stick in a way where you can't really wake it up. But on Intel x86 architecture, instructions don't have to be aligned, and therefore we can find this instruction as part of another instruction, because it's a very short instruction. You can see the data for it, the hex breakdown of it here. And then what we're going to do is we're just going to have move pattern execute and write a double word to an address of our choice, and then return to this jump pattern, and then we're going to use this again and again, writing one double word at a time until eventually we'll have whatever we want to store wherever we want it. Now, once we have this ability, we can think of many creative ways to achieve execution. Specifically, the blog post describes using this to write shellcode onto the stack, and then using virtual protect to make the stack executable, and then executing the shellcode. Atom bombing is an injection technique we published back in October of 2016, and it exploits the global atom table and APCs, which are async procedure calls. We actually witnessed this used in the wild by Dridex, which is a notorious banking Trojan. The way this technique works is that a malicious process, for example, can take malicious code and place it inside of the global atom table using an API called global add atom. Now, once this code is in the atom table, it uses async procedure calls to get a target process, which is a legitimate process for that matter, to retrieve the code from the atom table and write it to a read-write section in the address space of the legitimate process. At which point we use some return-oriented programming to allocate virtual memory that is executable, and then copy the shellcode from the read-write section to the executable section, and then finally we execute it. Now, these techniques that we just discussed all allow injection of code into a process that's already running, and in most cases malware authors are going to want to inject it into something like Microsoft executable that could be crucial to the operating system, or could be something that is used by the user, such as Internet Explorer. So that is something that if, for example, the malware crashes for some reason, it could crash the PC, and it'll easily get the attackers caught. So something that they would like to do is be able to run their malicious code inside a process of their own, that if it crashes, it has no effect on the rest of the system. And so this is where process hollowing was invented. Now, process hollowing works by creating a process in a suspended state. And so we have a process, and each process has a process environment block, which points to the main image that's loaded, and also we have the EAX register, which points to the first instruction that the process is going to execute, or the entry point. At which point we move on to unmap the section, the main image, and so we have sort of a hollowed process, and this is where this technique gets its name. As you can see, currently EAX points to nothing at this point. This is the time to allocate some memory that's going to be used by our evil executable, and then for each one of the sections in the evil executable, we're going to write it to the target process in the addresses that we allocated previously. So we can see that we're copying the data section and the text section and whatever other sections we need, and then everything we need to execute is now already set in the target process. At which point we can relocate the image if necessary. We can set the base address in the process environment block if we changed it, which is not necessary in this example. And then all we have to do is just change the EAX register to point to the correct place in the text section, and finally resume the execution. And so the process starts working, and it's basically a malicious process that's masqueraded inside of a legitimate Windows executable. So when this method came along, it was able to fool many security vendors because it was novel and wasn't detected. But nowadays, all security vendors are aware of this technique and are able to easily monitor and detect and prevent it. And the most trivial implementations of process hollowing actually just create read, write, execute sections, and that's easy to detect in numerous ways. If the attackers are a bit more creative and don't just copy the first example from GitHub, but actually unmap the main module and then allocate memory with correct protection, for example, then first of all, the unmapping of the main module is highly suspicious, and that's something that should be flagged by any normal security vendor. And also, we need to understand that every address in a process has something called a virtual address descriptor, or a VAD. And this virtual address descriptor, if we take a look at the virtual address descriptor of the start address of the main thread of the process, it should be of type image map, because that is how memory is mapped when you map an image. The type of it is an image map. Now, once we use a function that allocates virtual memory, then the type will not be image map, and so that is something that is suspicious as well. Let's say the attackers get even more creative and don't unmap the original executable, but just overwrite it in memory. So in Windows, there's a mechanism, an optimization mechanism, that when loading executables, they become shared among processes. And the reason for that is that if you want to load an executable a few times, then you don't want to actually have it stored in memory a few times. You want to store it one time and have all the processes share that memory. And Microsoft, through the PFN database, which is a structure that describes all the physical pages in memory, has a flag that says whether the page is shared or private. Now, when mapping a normal executable, that flag is going to be 1 for shared, and once anyone tries to write over that page, the operating system makes a copy of that page, and that copy becomes a private page. So the flag changes from 1 to 0. And again, that's something that we can check for and detect. If the attacker tries to unmap the executable and then remap as a non-image, then the virtual address descriptor again will not match. The type will not be type image map. And if they do what seems closest to a legitimate process and try to unmap and remap as a normal image, then at this point we can see that the start address is going to be different from the address of entry point of the image that's actually loaded. And also, if we take a look at the file object that is associated with the process, we can see that the virtual address descriptor that describes the actual entry point is the actual start address points to a different file, and so there we can also flag it. So as you can see, process hollowing is it's not so great anymore, given what we've just talked about, and the rest of the techniques we talked about, atom bombing, ghost writing, etc. They're all missing this file mapping property, which is something that is suspicious and easily detected by today's solutions. So we need something new. We need wouldn't it be cool if we could create some kind of fileless mapped file? But AVs scan files, and we need to understand very well how scanners work in order to try to bypass them. So for that, I'd like to call Eugene to talk about antiviruses and scanners.
So let's talk about how antiviruses scan files while they are being executed. So let's imagine the virtual execution process. When we want to execute the file, we first have to open the file, then we have to create a memory mapped section and map it to the virtual memory space of the target process, and then we have to actually start the execution. We'll cover some common scenarios when the AVs intercept the file execution and how they scan it. So let's see where the execution can be intercepted. So the first place which is usually available to AV vendors to intercept is during file open or NT-create file. At this place, the file is still not mapped into memory, but it can be scanned even before it's opened, and we'll see later how it's done. The second place where the file execution can be intercepted is during section creation. There is a special callback inside minifilter called require for section synchronization, which can intercept section creation before it's actually created. And the last place that we will cover is a process notification routine, which can, in the blocking version, be used for a main executable only. We'll talk about it later. So what else should be considered when AV vendors work on their products? First of all, they have to decide, once intercepted, how to scan the file. The file can be scanned from user mode, from kernel, or from any combination of the two. Also, the file has to be somehow accessed. So it can be reopened using the original file name from the original operation. File name could be taken and the file could be opened again. On some file systems there's a file ID, which is something very similar to file name. And of course, in the kernel, when you intercept the I/O, you have the file object. So the same file object can be used to access the data. So every vendor have to decide where and how to access the content of the file. You can easily imagine that if the file is being changed many times, rescanning the file after each change is not practical. If the AV will try to do it, probably your computer will do only the AV scanning and anything else will not work. So it's important to understand that it's not practical to scan always. We have to decide where to scan at distinct times. And of course, if we scan the file before the execution, we are blind to the changes which is done to the content of the file or the memory after the execution. So we are blind to other techniques that change the file after the execution starts. So let's see some examples. Let's start from opening the file. We can intercept the file open with an example from actual one of the AV vendors. We have taken partial stack only to show you the concept. Here the AV blocks the execution inside the mini filter when the integrate process tries to open the file. And meanwhile, in another thread, usually it's another process belongs to the antivirus. The antivirus tries to reopen the file and scan it. So you can see here the file is opened by file name. So this specific vendor has decided to use file name to reopen the file. Another example is interception during section creation. In this specific example, you can see that Microsoft Defender tries to scan the file while other vendor intercepts this attempt, blocks the memory mapping, and like in the first example, you can see that you can imagine that it will be scanned in the same way from another process, and if the file is considered to be clean, the execution will continue, otherwise it will be blocked. Some special notes about the callback acquire section for synchronization. In the user mode, we have many options to pass to the section creation. One of them is the section type, which is if you load the executable via a regular way, integrate process via Windows Loader, it will be sec image, and another parameter which is called page protection, which is expected to be page execute, because we want to map this section as execute. But it's actually what happens is that the mini filter doesn't receive the section type; it only receives the page protection parameter. And there is a feature in Windows that if you manually map section not via loader, you can pass here any other page protection than execute. You can still map the executable as with execute permission, but the callback routine will not receive the correct page protection. It will get the page protection that was passed from user space and not the actual page protection that will be used on the pages in memory. So AV vendors should be careful about this, examining this parameter to decide if to scan files or not. And the last place that we will cover is the pre-execution callback. It's in this example we can see the AV vendor was blocking the same create process at the last phase just before the thread is allowed to run. Again, it will be scanned as in the first example, but from the other thread, and if allowed, the execution will be resumed. It's important to know that this routine is available from Windows Vista and on in the version that it can block. In the previous Windows versions, there were other ways to intercept the execution, and the blocking version is not available for DLLs. It's only available for the main executable. And of course, as I said, it's blind process hauling, which happens after the execution, and there's nothing that can be done at this point. So let's summarize. There's a lot of problems that AV vendors have to face when they are creating their product. There are trade-offs between performance and coverage, and considering those trade-offs, it's understandable that AV tries to do their maximum to get the maximum coverage while leaving the system in the operational state, and so it can do something else besides AV scanning. We have different operating systems that will have to support, starting from XP to Windows 10. We have 32, 64 bits operating systems, different CPU types, different file systems to support, and all this makes things very complicated. But there are some other layers of complications that also adds to the complexity of the scanning process, and we would like to talk about transactional NTFS. So what is transactional NTFS? Transactional NTFS, also called TXF, it's a feature introduced in Windows Vista. It's implemented completely inside a NTFS driver running in the Windows kernel. It works only for local disks. It doesn't work, for example, for network mapped drives. The original purpose of using it was adding support for changes in multiple files as part of transactions. So all these changes can be either committed or rolled back as a single atomic operation. This transaction could be part of even larger transaction, which may include many applications. For example, Microsoft SQL Server. So you can do the single transaction across multiple applications, and the NTFS was part of this transaction. Today, it's mainly used in installers, so installation process could be simplified. You don't have to write the code to roll back all the files in all the stages of installation process. You can simply roll back the transaction and do. Of course, if you do everything inside the transaction, Microsoft Update still uses a transaction today to simplify the update process of the Windows. Yeah. Some facts taken from Storage Developer Conference slides available online. You can see that the NTFS driver was significantly changed to support transactions back in Windows Vista. There are a lot of new functions which were added to support Transacted API. We'll talk about them a little bit later. And many other functions were changed to support transactions as well. So one interesting fact that you have to know about the transactions is that they were deprecated very soon after they were released. So Microsoft advised you not to use transaction anymore since Windows Vista, and as usually happens with most deprecated features, it's still used today even by Microsoft. So let's see how we can use transactions. So application has to explicitly use transactions. It has to be written to use transactions. The transaction is created with a special function create transaction, and the transaction is ended with either commit or rollback. Those two functions end the transaction. For all functions that supports file name, you have to tell Windows that you want to use transaction. So there's a special version with transacted ending, which tells Windows that this function is part of transaction. You have to supply the transaction handle to those functions. For other functions which works with file handles, you don't have to supply anything special because file handle is also is already marked that it is part of a transaction. So Windows knows that it's inside transaction. Let's see some example how you can use transactions. So we create a transaction. we create a file inside the transaction, we write to the file, and we close the file handle. So, for example, if it was a new file which was not exist before the transaction created, and you at this point you try to find this file from another process, you will not see it because the file is created only inside the transaction. It's not available to any process looking from outside of the transaction, and only when you commit transaction, the file will be visible inside the directory where it is located. It's different from a regular file, which at the moment it's created without transaction, you can already see it by any other process in the Windows. And finally, transaction should be closed. So far we have covered some topics. I'll pass to Tal back microphone so he can continue.
So what do we have so far? Well, we took a look at the history of evasion techniques. We took a look at all the factors we need to consider when we are developing an AV scanner. We took a look at NTFS transactions, and you must be wondering what's next. Well, naturally, transactions make life very hard for AV vendors. And what we like to do is try to leverage transactions in order to create a process that is very hard to scan. However, we don't have a create process transaction API, create process transacted API, so we can't really rely on that to somehow pass a handle inside a transaction. So what we need to do is we need to dive into the process creation process on Windows to try to find a way to do it. And so what we're going to do is we're going to compare the create process function between XP and 10, and superficially looking at it, we see that there are many changes that have been introduced, and it seems like Microsoft almost completely changed how processes are created. That being said, a deeper examination shows that Microsoft simply moved most of the code from kernel 32 subsystem library in user mode to the NT kernel, and somehow the function in kernel 32 became longer. So logically, the steps remain mostly the same, at least for our purposes. So we're going to take a look at the create process on Windows XP, and we're going to take a look at this in the assembly code. And if you don't know assembly, that's okay. You just take a look at the words we're seeing here, and everything is commented, and I'll explain every step as we go along. So we can see that create process is just a wrapper around an internal function that the first thing it does is it tries to open the executable file. The next step is to create a section by calling the system call ntCreateSection. Now, as you can see, the section type that's being passed is secimage. This means it'll map an image file, so it'll be executable, and the page protection is page execute. Now, as Eugene said before, this is not a must. If we call ntCreateSection ourselves, we can specify page read, and that's what's the mini filter callback of the antivirus will see, and so it won't scan this section. The next step is to call ntCreateProcessEx, which is a system call that will actually create the process in the kernel. Now, what's important to note here is that the parameter being passed here to create the process is the section handle, not the file path. So the file path doesn't make its way to kernel mode. Just the section handle that's already an object that can be mapped directly into memory. Now, let's take a look at what happens in the kernel routine. We can see that we use the object manager's create object routine to create the process object, and then we add the object to the list of running processes. At this point, we return back to user mode, where we need to discuss something called the process parameters. Now, every process on Windows has a structure called the user process parameters, and this structure contains crucial information for the process to run, and the process simply cannot run without it. And an example of something that lies within the process parameters is the command line of the process. Now, this routine here, called base push process parameters, will actually create the parameters, as we can see here, by calling create process parameters, and then it will allocate memory in the created process for the process parameters, and then it will write the process parameters to the remote address space, and finally it will set the pointer to the process parameters inside the process environment block, and that is how the process knows to reference the process parameters. Now, what's important to note here is that this happens after the process has already been created. So the process first gets created, and then we create the parameters and write them to the created process. At this point, we need to create the main thread for the executable for the process, and then finally, if the flags specify, we resume the thread and basically start the execution of the process. And we return. Let's take a look at create process on Windows 10. As we can see here, it's also a wrapper around an internal function. So let's take a look at that, and we can see that the first thing that happens here is actually we create the process parameters. So we call the routine to create the process parameters, and then we fill the parameters with some data. But what's interesting to note here is that this happens before we create the process object, in contrast to Windows XP, where we saw that the process is first created and then the parameters are created and copied to it. So here we see that the process parameters are created, and only then do we call the kernel to create the process. Now, what's interesting also to note here is that we do not open the file in user mode before passing control to the kernel, and we do not create a section for it. So in Windows 10, we use this nt-create user process, which is a new system call introduced in Windows Vista, and this receives a file path and not an already existing section object. And so the kernel will actually open the file for us. The other thing that's being passed is the process parameters, and that means that the kernel is going to take these process parameters and actually put them in the created process's address space itself. So it's no longer the user mode's job to do this after the kernel creates the process. Now the kernel does this as part of the process creation routine. So let's take a look at what the kernel routine does. We can see that it first tries to open the file, and then it will create the section just like as an XP, except now this is all happening in kernel mode. Once the section is created, we copy the parameters from user mode to kernel space, and then we move on to the routine that is in charge of allocating the process. And we can see again the create object routine of the object manager, which creates the process object. And then we can see the kernel allocating memory for the process parameters. Using memcopy, it copies the parameters to the created process's address space, and finally it sets the pointer in the process environment block to point to the process parameters. The next thing that happens is we allocate the main thread of the executable of the process. We insert the process and the thread into their respective lists. At this point, we will have the dispatching of the create process notification routines that Eugene mentioned before. And then we return to user mode, at which point all we have to do is, if this flag specify it, we resume the thread and the process starts executing. So to sum up, let's take a look at the main differences between the process creation process on Windows 10 and on Windows XP. We can see that on Windows 10 we use the system call nt-create user process, while on XP we use the nt-create process ex system call. Now nt-create process ex receives a handle to a section, while nt-create user process receives a file path. It's important to note that this means that in Windows XP the user mode is in charge of creating the section from the file, while in Windows 10 the kernel does this. Now, nt-create process ex, the XP routine, is still available in Windows 10 because it's used in the creation of minimal processes, which is beyond the scope of this talk. All the supporting user mode code, however, is not available post Windows XP, and so we need to implement it ourselves and to do all the heavy lifting ourselves. So, doppelganging. What we want to do is we want to load and execute an arbitrary executable, and we want to have this run in the context of a legitimate process. We want to use none of the suspicious process hollowing API calls such as unmap view of section, virtual protect, and so on. And we want the AV to scan clean files only, or to not even scan us at all, and we want to be able to evade advanced forensics tools. So we break doppelganging into 4 distinct logical steps: transact, load, rollback, and animate, which is to bring the doppelganger to life. What we do is we first create a transaction, just like in the example that Eugene showed before in NTFS transactions. Then we open a clean file in a transaction, such as a Microsoft binary, for example, SVC host. And now we have a nice clean green file object here on the right that is completely clean and no antivirus is going to flag it. At this point, we're going to overwrite the file with malicious code. And so this file object sort of gets tainted with malicious code. However, I'd like to remind you that we're inside a transaction, so anyone trying to inspect this file will not be able to see the changes that we've made because they're outside the transaction context. At this point, what we're going to do is move on to the load phase. The load phase is basically to create a section from the tainted file and have that section point to our malicious executable. And so we have a section created from the transacted file. At this point, we can move on to the third step, which is rollback. Now, rollback simply undoes the changes that we made to the file. Before, when we talked about NTFS transactions, we described the transaction ending in two ways. Either the transaction succeeds, and so you commit the transaction, or it fails and you roll back the transaction. In our case, we roll back regardless because we would like to undo the changes we made to the file system. So once we do that, we now have a clean file object again, but the section still has the malicious code that we wrote to the file originally. At this point, we move on to the last final step, which is to create a process from this section. And we use the information we uncovered before from examining the Windows loader, and we use the ntCreateProcessEx routine to create a process from this section object. Once we do that, we now have a process that it looks legitimate and actually runs malicious code in it. We also need to create the main thread for the process, and then all that's left is to do the rest of the heavy lifting that used to be done by the user mode code in Windows XP, which is to create the process parameters, to allocate memory for the process parameters, to fill the process parameters with the correct values, to write them to the target process's address space, and then to set the address of the parameters inside of the process environment block. The last thing we need to do is to resume the execution of the thread and basically have the doppelganger start running. Let's take a look at this live in a demo. Okay, so as you can see, we have a fully updated version of Windows Defender. It's updated to December 6th. Today is December 6th. And what we're going to try to do is we're going to try to run a tool called Mimikatz. Now, this is a password dumping tool that we don't think is malicious on its own, but when combined with the threat actor, could be used for malicious purposes. However, Defender does seem to think that this is a malicious tool, and so let's see what happens when we try to double click it. We can see that Virus and Threat Protection has notified us that threats have been found. So what we're going to try to do now is we're going to create a doppelganger of MS Paint, which is the paint utility that comes with Windows, and it's going to host a Mimikatz from an encryption file on disk so that Defender cannot scan it. And so let's try and see what happens. And as we can see, Mimikatz was able to run. Defender is okay with it. This is a fully functional version of Mimikatz. As you can see, the icon was preserved from MS Paint, but everything else is Mimikatz. If we take a look at Process Explorer, we can see that we have no Mimikatz running, but we do have MS Paint running. If we take a look at the properties for this process, we can see that it's running MS Paint. Everything looks legit. So we ran this demo program on Windows 7 and everything worked well. And the first time we ran it on Windows 10, we got a blue screen of death. And when we looked online, we saw that this crash was actually reported by James Verschaw. And it happens because of an null pointer to reference where null is being passed to the system call, and then somewhere down the line it tries to reference the data there, and it crashes. So fortunately for us, though, Microsoft was nice enough to fix it for this talk. So this bug was introduced in Windows Redstone, and it was fixed in the Fall Creators Update that was released just a month and a half ago. So we could now present the demo on the most up-to-date Windows 10 release, which was not possible 2 months ago. Now, the affected products are actually all the antiviruses we tested this against. This is a full list that we have. As you can see, all the major vendors are here. They simply just don't know how to handle transactions the way they should, and that's why this is able to bypass. Now, if we talk about detection and prevention of this attack, so what we could do is scan using the file object that is available in the create process notify routine, and this is available on Vista and up, but the technique is only relevant for those operating systems. And if we get an error while trying to read from the file, then we can block because we know this is something that shouldn't happen. But this won't work for doppelganged DLLs, and so we need to find some other way to scan those. So the option we have is to scan all sections, even data sections, because the flags that we get in the minifilter callback are misleading. So we have to scan everything, but this is a huge performance issue to consider. When talking about forensics, if you want to detect process doppelganging, then we can take a look at the file object associated with the process and see if it has a write access enabled, and if so, then we can infer that that probably doppelganging had taken place. And another thing we can do specifically on Windows 10 is we can take a look at the image file pointer field of the eProcess, and if it is null, then we know that something fishy is going on here, which could very much be doppelganging. So to sum up, process doppelganging allows you to take a malicious executable and then create a process out of it, but making the process look like a legitimate process. It uses the Windows loader, so there's no need for a reflective loader or a custom loader or anything of that sort. The image is mapped correctly to an image file on disk, just like any legitimate process, and we don't have any of the unmapped code, which is usually associated with modern malware nowadays and is detected by modern AV solutions. We can also leverage this technique to load DLL files, and this technique is completely fileless. Now, even the most advanced forensics tools such as volatility will not detect it, and it works on all Windows versions since Windows Vista. And note that it bypasses all the tested security products. Special thanks goes out to Omri Misgov and Udi Avo, who helped us a lot with the research, and this presentation would not be possible without their help. So thank you very much, and we'd love to address any questions.